Comin. Riccardo, are
I'm
you
here.
online? Ah, there
Yes.
you are. Please share your
Um,
screen. We see you, yeah, the view and the pointer. So Riccardo Comin, MIT, P-wave magnetism and spin spiral magnets. Please, Riccardo.
okay. Thanks, Yaron. Thanks to all the organizers of this conference, and greetings from the northern Adriatic Sea. As you can see, I'm here in a bit of a weird setting because I'm sitting at the bottom of a bunk bed in my grandfather's summer house, not far from my hometown here, and I'm here on special permission from my wife and kids, which is the reason why I can't stay here a lot longer. But I just wanted to say it's a great pleasure to have a chance to speak to this audience and to your physics community over there. And for what it's worth, I think it's fantastic that you're having this meeting and this conference. And I'm really happy that I had a chance to participate and tell you a little bit more about this exciting topic. So my talk will be about P-wave magnetism. I wasn't here for Jairo's talk, so he might have said a few words about this already. But here's essentially the outline of my presentation. So I'll start with a little bit of a background and introduction on not so much on ultramagnets because we've had already a few talks that have kind of laid out the broad canvas on this new nascent field. But I'll talk about specifics of non-collinear systems, especially spin spirals, as a platform for out parity magnetism. And this is still like kind of like a form of unconventional magnetism. So a form of magnetism where the spin splitting is governed by non-relativistic effects, unlike many other systems where it's governed by spin-orbit coupling. But this is a magnetism that has a little bit of a different symmetry properties than the conventional collinear altermagnets that were already discussed. And then I'll discuss a specific realization of this form of magnetism, which is this helimagnetic material, nickel iodide, which is both polar and chiral, and it's also multiferroic, and so which presents the opportunity to control the magnetism electrically. And then I'll talk a little bit about how we realize this kind of P-wave magnetism there and how we can control it using electric fields. So before I get started, I'm the marketing guy, as you all know. So I'm just here representing the people who actually did the work, and in particular, I want to give full credits to this young fellow Cheng Song, who's been a phenomenal driving force for this project. He's basically carried through the project in almost all its components, from the material synthesis to the optical experiments and the device fabrication and also some symmetry analysis. So he's really being outstanding. And then many collaborators, in particular, I want to highlight the group of Silvia Picozzi, who did, and specifically Serjan Stavric, they did all the DFT calculations in support of this work. So, okay, this is my only slide on altermagnets. So I just want to basically sort of recap very quickly. So the idea is that before a few years ago, we had a broad understanding of collinear magnetic systems as being essentially divided into main classes. One is ferromagnets, the other one is antiferromagnets. And in ferromagnets, of course, you have net magnetization, PT symmetry is broken, you have a uniform real space spin density, so it's Q0 order. And you also have uniform K-space spin splitting. So you have spin majority and minority bands. In the antiferromagnets, on the contrary, there's no magnetization. So you have a perfectly compensated system. PT symmetry is unbroken. And this in the conventional antiferromagnets. And then the spin density is spatially modulated. So these are finite Q spin orders, and then there's no spin splitting in K-space, which is just a reframing of the general statement that's encoded in Cramer's theorem. So you have Cramer's degeneracy. And then, since a few years, and thanks to people like Jairo and Libor Schmeichel and Thomas Jungfirth, we come to the realization that there's a new class of magnets which kind of has properties that are sort of inherited from both of these. So you have a new class of magnets which are perfectly compensated, so zero magnetization. But in these systems, PT symmetry is broken, and so the spin density is spatially modulated. And but importantly, there's no Cramer's degeneracy, which means that there's a non-uniform spin splitting in momentum space. And most importantly, especially in thinking about device applications, the spin splitting is governed by the exchange interaction between the conduction electrons and the local moments that form the magnetic order. And this is usually much larger than, let's say, Rashba effects, which are governed by spin-orbit coupling. So we're talking about hundreds of milli-electron volts up to maybe few electron volts energy scales for the spin splitting. And of course, because the spin splitting is non-uniform in K space, you have these kind of different form factors that tell you how the spin splitting or the spin polarization density in reciprocal space varies. And these are even parity states, so you can have D wave, G wave, or I wave. Those are the only ones that are compatible with point symmetries in crystalline systems. So you have these two main classes now. So we have the alter magnets, which are zero magnetization, but they have this kind of spin polarization that's modulated with this form factor. And then you have the ferromagnets, which have a spin splitting which is uniform. So we can think of those as S wave. And in the middle, of course, we can now extend this kind of classification and think about systems that have different kinds of form factors, including some that are alt parity. And one example is P wave magnets. Now, it turns out that P wave magnets cannot be realized in collinear systems. They require non-collinear materials. So spin-orbit coupling does play some kind of role in these systems because it has to set up the non-collinear magnetic ground state in the first place. But once you have that, and if you have the right symmetry properties, then you can end up in a situation where the spin splitting changes sign when you revert momentum along a certain direction, giving you one nodal plane, or perhaps three nodal planes, but in any case, an odd number of nodal planes in the band structure. Okay, the P wave case would be one nodal plane. So in S wave and D wave magnets, they generally have even parity spin polarization. This usually requires currents for switching, although there are some developments on the front of ferroelectric alter magnets, which may present new opportunities. The P wave magnets are alt parity. And most importantly, if there is bilinear coupling between the spin and the charge, which usually there is in many of these non-collinear systems, especially spin spirals, then if this coupling is allowed, then that can present an opportunity to control the systems electrically by virtue of the spin polarization state already breaking inversion symmetry in the first place. And so what we're looking for is essentially these four ingredients. We want inversion symmetry breaking. We want a switchable electrical polarization, so ferroelectric order. We want a non-collinear magnetic order in the background, and then we want strong magnetoelectric coupling. So a great platform to realize all of these ingredients is spin spiral or type 2 multiferroics. So type 2 multiferroics have been known now for over 2 decades. Now the prototypical example is a spin cycloid. So this is also known as a longitudinal spin spiral. So longitudinal spin spiral because the spin rotation plane contains the propagation axis of the spiral. So and spin cycloid is not chiral because it has at least one mirror plane, but it does have an handedness. And when you revert that handedness, you can revert the associated bond polarization in the system. Okay, so an inversion operation can change the handedness of the spin cycloid and can revert the ferroelectric order. Now, how does this ferroelectric polarization arise? Well, it's essentially from spin-orbit coupling, right? So this is a ferroelectric polarization, which is also known as the bond polarization. It's a polarization that's in the charge degrees of freedom, primarily, and then secondarily it can be in the motion of the ions, but primarily in the charge degrees of freedom, and it's associated to pairs of spins that have a finite spin chirality because they have a non-zero angle between them. And this is enabled by spin-orbit coupling via in this specific case of the cycloid, via the Zaloginsky-Moria interaction. Okay, so there's a spin-orbit coupling that activates basically an off-centering of the electronic clouds that gives you an improper ferroelectricity. So ferroelectricity purely of electronic origin. And this has been beautifully demonstrated or discovered the first time in 2003 in Tokura's group by Kimura-san in the manganites, where they observed that there is an electrical polarization that arises concomitantly with a magnetic transition. So at the Néel temperature in these systems, you have an electrical polarization, and importantly, you can tune this electrical polarization with magnetic fields, which is a direct signature of magnetoelectric coupling. So another example of a spin spiral is a spin helix. So a spin helix is a transverse spin. It's a transverse spin spiral. So now the spin rotation plane is perpendicular to the propagation axis. In the spin helix, the Zaloginsky-Moria is zero by symmetry, so it's silent. But spin-orbit coupling still has additional terms that it can contribute to give you a bond polarization. And one example is the spin-dependent PD hybridization. So there's a different expression for the polarization that's associated to pairs of spins. And this is now non-zero in spin spiral systems. And This was shown also about 15 years ago in a different class of materials. This is manganese iodide, which is a dihalide. It's a triangular lattice magnet, which is very similar to the material I will discuss today. And here again, you see that at the magnetic transition, the helimagnetic transition, there is an electrical polarization that arises. And again, the electrical polarization is tunable by magnetic field. So the cycloid is polar, but not chiral. The helix is both polar and chiral. And so there's potential for voltage control of chirality and spin polarization. And it turns out that these two are very closely related, as I will discuss later. Okay, so this is the specific material we've been looking at. This is a system that we have studied for now many years, for at least 5 years. It's a material where we've discovered a multiferroic state all the way to the ultra-thin limit. So this was our original study. And then more recently, we've focused on this kind of realization of P-wave magnetism. So nickel iodide is a triangular lattice layered magnet. So it's a van der Waals material. So the layers are weakly coupled between each other. So these are the nickel iodine 2 layers. It's a magnetic insulator. And if you look at the lattice from the top, you see that the nickel atoms, which are spin 1 magnetic ions, they occupy the sides of a triangular lattice, and then they're octahedrally coordinated to the iodine. So this is a kind of edge sharing network of nickel iodine 6 octahedra. And at high temperature, the system has fairly high symmetry. So it's a rhombohedral structure, R3 bar M. So it has inversion symmetry. So there's an inversion center here. It has 3-fold rotational symmetry. It has 3 two-fold axes and has 3 mirror planes. So very, very high symmetry structure, basically the realization of an almost perfect triangular lattice system. And what's interesting is the spin physics in this material, because there are this spin 1 magnetic ions at the nickel sites, which interacts through exchange. And even though, I mean, the triangular lattice is, of course, a platform for frustration, but that requires an antiferromagnetic nearest neighbor exchange to be dominant. But this system, instead, the nearest neighbor exchange, the first nearest neighbor exchange is actually ferromagnetic. So it has a negative sign in the exchange constant. But interestingly, what happens is that the second nearest neighbor exchange is basically negligible, but the third nearest neighbor exchange has the opposite sign and almost the same magnitude. So this creates the perfect conditions for realizing a non-collinear state. So now your spins don't know if they want to be parallel on the nearest neighbor bonds or anti-parallel. They cannot quite solve this kind of frustration. So this leads to a state where we develop these spin spirals. So you have this kind of non-collinear spin state with these helices that have a propagation direction which is, partly in plane and partly out of the plane. So it's kind of like at an angle from the planes, but it's a proper spin helix with a spin rotation plane perpendicular to the Q vector. And this transition to this helimagnetic order occurs at around 60 Kelvin in the bulk. You see the very clear signatures in the susceptibility. So you see a kind of like a step-like transition at this temperature. And then concurrently, if we measure the electrical polarization, for instance, through pyroelectric current measurements, you see a sudden jump in the polarization. So this is a very sharp transition. We think it's a first-order transition. And when you reverse the cooling field, then you see that the polarization reverses. So the system is both magnetic and ferroelectric, so it's a multiferroic, and the two autoparameters are strongly coupled, and so it's a type 2 multiferroic. We measure the magnetization as a function of field. There's no weak ferromagnetic moment in the system, even though it's potentially allowed by symmetry, but we just don't see it experimentally. So as far as we can tell, this is a perfectly compensated magnet. So we can look at the spin helices using resonant magnetic X-ray scattering. So just to convince ourselves that the spin helices are real. So we can see these diffraction peaks at with an in-plane wave vector component of about 0.14, 0.15 reciprocal lattice units. So this is a spin helix that has a pitch in real space of about 7 unit cells. And so we see that these diffraction peaks that show finite circular dichroism. That's because of the chirality of the spin helix. And then the temperature dependence shows that this basically serves as the order parameter for this particular state. So it dies off at 60 Kelvin as expected. And we can measure the electrical polarization, and we can perform electrical switching all the way into the thin limit, in fact, all the way into the monolayer limit. So the way we do it is we use bulk photovoltaic effect because it's very hard to do a pyroelectric current measurement in that limit. So instead, what we do is we illuminate with... I'm I'm hearing some turn. I think so. Okay, no, that's good. Thank you. So we illuminate with the laser, we create photocarriers, and then the internal polarization field of the material that acts as essentially as a built-in electric field. So this is like a PN junction of sorts, but it's a bulk PN junction. And then this leads to a photocurrent because it splits the electrons and holes in different directions. And so we can realize these simple two-terminal devices where you can collect this photocurrent, and that gives us a measure of the polar order or the ferroelectric order or this built-in polarization. And we can see again that with opposite field cooling, we get opposite sign photocurrent, which is a direct signature of this polar state. We can do this as a function of temperature and as a function of electric field. So we can do the full switch in the full ferroelectric hysteresis loop. So this kind of works as a very conventional improper ferroelectric. So now then the important question is why spin spirals are p-wave magnets, which is mainly what my talk is about. Maybe before I get to that, let me ask the chair, how much time do I have left? 10 minutes?
9 minutes.
9 minutes. Okay, great. So let's look again at this spin helix. Okay, this is a one-dimensional spin helix. Now we're forgetting about the lattice of nickel iodide specifically. This is just a spin helix living on its own. And this is a right chiral spin helix, okay? So with the spins rotating in a certain direction. And then if we imagine a conduction electron present in the system that travels through the spin helix, and if we now take the perspective of the conduction electron itself, the conduction electron is moving into a background which has this sort of like helically arranged magnetic moments, which is kind of like a spatially modulated magnetization with a helical pattern. And what this does effectively at like at the level of the wave function of the system is it introduces a Barry phase, which translates into an effective emergent magnetic field from the perspective of the electron itself. The Barry phase is essentially due to the fact that the local spinner for the conduction electron tries to adjust to the local magnetization through exchange coupling. And so this introduces a phase in the wave function of the electron during its motion. And this phase is an effective vector potential. So we can also think of this as if we sit on the electron and we take the perspective of the electron, from the perspective of the conduction electron, what it sees is it sees a magnetic moment that precesses. And so the question is then, well, if you have a precessing magnetic moment, you must have a field that applies a torque to that magnetic moment. And that's exactly this effective field that the electrons feel during their motion through the helix. And this is essentially an inverse Larmor precession of sorts. If you now take an electron going in the opposite direction, you will see the moments sort of revolving around in the opposite direction. So the field will change sign for an electron moving in the other direction. So now we have a linear relationship essentially between momentum and the field. And what that produces is it produces and most importantly, the field is in the direction of propagation of the electron, which is in the direction of the helix. And so what that will do is it will produce essentially a spin splitting or a Zeeman field, which is momentum dependent. And it's positive, let's say, for electrons in the positive k direction and negative for electrons in the negative k direction. And so this will give you this kind of p-wave textures because this Zeeman field will promote or will shift down in energy spin down states on the left and will shift down in energy spin up states on the right. If we reverse the chirality of the helix, because these are rigidly coupled, this effective magnetic field and the chirality, this will reverse the spin polarization texture in reciprocal space. So now you have the same p-wave spin polarization texture, but now with the opposite sign. And that's because, again, these magnetic fields now switch sign when you switch the handedness of the helix. And what's important is that the size of the momentum splitting that this kind of momentum-dependent Zeeman field gives you is proportional to the Q of the helix. So the shorter the period, the larger the momentum splitting will be, which means that the larger the energy splitting between these spin split bands will be. Now, we looked at this from DFT first. So this is a calculation without spin orbit coupling. And what you can see already is in the direction that's along the Q vector of the helix. One thing I should have mentioned clearly here is that this axis here, this horizontal axis along which you have the p-wave spin polarization is the axis of the helix. So this is parallel to the wave vector of the helix. Whereas the axis that's or the plane that's perpendicular to it, that's the nodal plane. Okay, so that's the plane that in the case of nickel iodide contains the ferroelectric polarization. So what we're seeing in the calculation for nickel iodide specifically is that along the direction of the helix, we see this very clear spin splitting of order 100 to up to 200 milli electron volts, even in the absence of spin orbit coupling. And this spin splitting is only active along one direction. If you look at the perpendicular direction, you see that basically in that direction there is no spin splitting. So this is basically a direction that's contained in the nodal plane. And if we look at now the sort of like a constant energy contour of the bands with the color indicating the expectation value for sigma z, which is the spin in the direction of the helix, then we have here the q-axis is the vertical axis, and we see a reversal. So we go from blue to red, red to blue. So there's this odd parity texture along the direction of the helix, as expected for a helical state. Whereas in the perpendicular direction, which is the one of the ferroelectric polarization, the ferroelectric polarization I forgot to mention is perpendicular to the q of the helix, then this there's no but this is a nodal plane, and you can see that already from the fact that this is basically along this direction it's even parity. We reverse the chirality, we get an exact reversal of the spin texture, again as expected by symmetry. So the DFT very much confirms a simple picture even for this the specific reality of this material, and so already we can tell that at least from theory the material is a p-wave magnet. But the question is that can we show this experimentally? Like, can we prove experimentally that this kind of spin polarization texture in momentum space has this p-wave character? And so one way to do it is to perform a circular photogalvanic effect measurement. So what we're doing is we're exciting electrons in the material across between the valence and the conduction band, let's say, with circularly polarized photons. Now, circularly polarized photons have finite helicity. They carry angular momentum. That angular momentum is transferred to the orbital degrees of freedom, and then through spin-orbit coupling is transferred to the spin degrees of freedom. So we have basically that the circularly polarized photons are sensitive or are a probe of basically the difference in the spin angular momentum values between conduction and valence band. And so in the case of, let's say, right-handed circularly polarized photons, you will primarily excite transitions between spin down valence bands and spin up conduction band, whereas for left circularly polarized photons, you will do the opposite. So you promote primarily transitions from a spin up valence band to spin down conduction band, which means that one helicity probes electrons primarily of positive momentum, let's say. So it creates creates electrons in the conduction band for positive momentum, whereas the other helicity creates electrons with negative momentum. So they will produce a current which is positive in one case and negative in the other case. So when you take the difference, you see a difference in the photocurrent, which is the definition of the circular photogalvanic effect. And when you reverse the chirality, you expect an exact reversal of this effect. So these are these four terminal devices where we probe the circular photogalvanic effect. They're a very simple device. We have two sets of terminals because we want to apply a field both in the direction of the polarization. Well, we want to apply a field in the direction of polarization to polarize the material into a single chirality. So we have a helix with a single chirality because otherwise we would have domains, and so the circular photogalvanic effect would average to zero. And then we want to probe the zero bias photocurrent along both directions, both along the direction of the helix and along the direction of the ferroelectric polarization. And so this is the measurement. This is now for opposite field cooling. Say negative field cooling gives you left chirality, and positive field cooling gives you right chirality of the helix. And we see a clear difference in the amount of photocurrent for circularly polarized left and circularly polarized right lights. So this is the polarization here, which is at the angle of a quarter wave plate. So you go from linear to left, back to linear vertical to right, and then back to linear vertical. So you see this very clear kind of difference between these two. And this difference reverses when you change the chiralities, when you do the field cooling with the opposite field. And this effect goes away with temperature. At basically at the highly magnetic transition at 60 Kelvin, this effect is gone. So here you see like the switching between left and right circularly polarized light, and you see the switching in the photocurrent. So this is the contrast mechanism. That's a direct probe of the P-wave spin polarization texture. And most importantly, like the important sanity check is to make sure that if we probe the photocurrent along a direction which is in the nodal plane, we should expect basically zero circular photogalvanic effect, because in that direction, we don't have any spin polarization. So the left and right circularly polarized photons will not be able to distinguish between positive momentum and negative momentum because there's no spin splitting. And indeed, what we observe...
2 minutes, Hawan. Okay, go.
I'm 2 minutes over time. Sorry, I have one more slide. I think I'm basically done. Yeah, thanks. So, and in that direction, you see that basically there is no contrast between left and right circularly polarized photons. So we have exactly the same photocurrent. So the circular photogalvanic effect is exactly zero. And that again, is the very direct probe of this P wave texture. Yeah, so this is pretty much the end of my talk. So we essentially we have been studying this material. We have I think we have conclusive evidence that spin spirals are a good platform to realize P wave magnetism. It may depend a little bit on the details of the crystallographic structure that the spin spirals are embedded in, and whether that supports the right symmetries to protect the spin polarization texture. In the case of nickel iodide, this works because there is one two-fold symmetry left at low temperature in the magnetic phase that protects the spin wave, the P wave spin polarization. And so we have the state which is highly magnetic and multiferroic. We can control using electric fields at chirality, and we can basically demonstrate the switchable out parity textures, which could have potentially device applications in the future if we can realize this at more reasonable temperatures. And that's all I have, and thanks for having me, and I'll be happy to take questions.
Well, thank you very much. Very nice talk. Questions online or in the audience? Let me start. So you point out very nicely there is the automagnetism, let's say, in the electronic sector, right?
Yes.
The first Cairo pointed out that much of this automagnetism also carries over to the purely magnetic sector, so to the magnons. So did anybody work? Did people look at let's say the magnons of P wave automagnets?
That's a good question. We've been so we have some resonant inelastic X-ray scattering data looking at magnons in this material from a while back actually. So we've actually been looking for folks in the theory community to kind of look at magnons and let's say magnum properties from more like a modeling point of view, but we haven't done it ourselves. We haven't really found anyone to collaborate with on this particular topic, but I think it would be very interesting for sure. As to the question of whether the P wave symmetry is encoded in some way in the magnon spectra, I'm not sure. I really have no idea. I think it's a very interesting question, and we already have data. So if anyone wants to look at it, we'll be very happy to collaborate on that.
Me, I want to collaborate.
Great.
Asle.
Hi, Riccardo. Great talk. Oscar Sudbe.
Hi, Asle. Yep.
So I can comment on this. I mean, for the ultramagnets, the collinear ultramagnets, we do have some results from magnons, which indeed show D-wave symmetry. And if you have these non-collinear magnets with some number of spins in a magnetic unit cell, at least you expect equal number of magnon modes as you have spins in your unit cell. So this could be a rather large number, and but I would certainly expect them to have this sort of symmetry that your original magnet has, based on my experience from ultramagnets.
Yeah, so that's a very good point. Yeah, and the material has an incommensurate spin spiral, so the magnetic unit cell is infinitely large. But we do see some magnon modes in RICs that disperse in a way which seems like acoustic-like. So I don't know if that's a special mode that we're seeing in those measurements. We see some electromagnons in Raman, so modes that have both magnon character and sort of dipole oscillation character. And but yeah, I agree. It could be definitely more complicated than in the collinear systems, but would be nonetheless very interesting to look at.
Yeah, one would look, I think, at the circular the circular
dichroism
of the RICs in this. We can talk about it.
Yeah.
So very nice talk. We have to close now. Thank you again. Thanks to all speakers of this morning.
Thank you.
Thank you, guys.